Hey guys, quantum computing is the next frontier, but it's a somewhat daunting topic. Now, I've always wanted to do a video where we explain quantum computing in nice terms for the average person, but I needed to find the right person to do that. Perhaps, I don't know, somebody with a PhD in physics. I've got exactly the right person coming up next after the video, so stay tuned. Happening
Quantum,
everywhere. If I've got this bottle of water, it's composed of atoms, and
right.
describe it for the viewers, right? So here's a bottle of water. It's made up of atoms, but at the atomic level, the principles of quantum physics apply, right?
Right, exactly. And basically, so quantum mechanics, it's this branch of science, right? That's basically models the dynamics of any system that is super, super small, super isolated, and normally super cold. So they work under these totally different laws. It's not like macroscopic on our level that it's not like you and I are quantum, but like you said, those like atoms in the water, in those it's the water molecules, those are operating on quantum mechanical laws, which is like really cool. Like basically quantum is everywhere. And that's also like motivation for why it's so important to study, you know?
Hey everyone, and welcome to today's video where I have a very, very special guest. I'll be interviewing Kimara Naicker from the University of KZN, and she's a physicist and a researcher in quantum physics. We're going to be talking about quantum computing. Kimara, a very warm welcome, and thank you for being here today.
Hi there. Yeah, it's great. Thank you for offering this opportunity to me and having me here. And I'm happy to chat all things quantum computing today.
Excellent. So I'm going to take it very slow. It's a bit of a daunting topic to us non-physicists.
Yeah.
But let's start with a bit about your background. Tell us a bit about yourself and how you got into this field of study and research.
Cool. Yeah. So I'm at UKZN, like you said. Currently I'm doing my PhD in physics. I'm part of the quantum research group there, and my research mainly focuses on classical machine learning and the application of machine learning techniques in general to something called open quantum systems, which we can chat about but later. Going further back, I'm from Durban. I went to high school here, did my undergrad at UKZ and also in applied math and physics, honors in physics as well. A lot of physics. It's always been physics for me. That was the only thing that was certain. And as I progressed through my studies and I found, started adventuring, researching more branches of it. I knew like, wow, quantum physics, this is like the thing that I really like, that gets me. And then much more recently, actually, there's so much development in the field of applications of machine learning specifically to this quantum physics. And so it's not just theory, like in a book anymore, a whole lot of equations or papers you've got to read. Now there's real world applications, which makes it so much more interesting to study. So yeah, that's me in a nutshell.
That's very
Academically.
exciting. I'm gonna come back to the machine learning piece. That's actually of
Okay, cool.
particular interest to us, right? So let's start.
Right.
I'm going to start with a very simple question, maybe perhaps too simple. I'll leave the answer to you to be very open-ended, right? For the person that isn't really familiar with the subject matter, what is quantum computing?
Okay, cool. So maybe like to me, or maybe like spending so much time with like people in my research group or people, it's studying the field. Basically, it's like you very rarely like come across someone like asking you this question, which I'm really cool. I'm really like happy to chat about it. So yeah, basically so classical computing, right? It's everything is stored in like bit strings of zeros and ones. So the analogy to that in quantum is now you have zeros and ones, but now there are some basic principles of quantum mechanics and there's laws of quantum physics that change the way these bits act. So firstly, we convert now into this qubit, the calling it qubit, a quantum bit basically, and it behaves differently to your classical bit. So here, they are ruled by these laws of physics that I mentioned, and some cool properties of them that are make them really useful and helpful in are basically superposition, entanglement, and interference. Those are three like major things.
Nice.
So if I just like chat about each of them briefly, it's like superposition is basically you can have not just strictly one or strictly zero. Now it can be both in a state of 0 and 1 at the same time, which is really amazing. And then entanglement is something like I can have like a qubit here, or like it's like two different systems. And when they are entangled, so you can entangle them in a certain way, we'll get to that later. But once they are entangled, they can be like infinitely far away. And if I do a measurement or do something to one system, you can find there's a way to find information about the coupled system, which is really cool also. And it has its benefits in certain scenarios. And then the last thing is interference, which is basically like kind of like sound waves or waves in general that we know of classically. So it's the same analogy that when you have waves, and if you superimpose them on each other, like you stack them over each other, basically, you can either like through their amplitudes or their phases, you can emphasize some waves. So like the amplitudes can get higher and higher, so that those stand out more. And then the ones that basically the ones that we don't want, they can interfere, deconstruct, and cancel each other out. So these are just like three of the properties that make quantum computing quantum, basically.
I want to deep dive into all three of them, but let's just rewind to what you said at the beginning, right? So we're using qubits, not normal bits. I guess a lot of people watching the video are very familiar with classical computing, which that's the first thing. All the computing up to now going forward will be known as classical computing. It's quite funny because what you're trying to say is that my entire, or somebody who did a BSc com science, their entire 3 years of varsity 20 years from now will just be a few subjects, classical computing, and we might have this whole world of new subjects, right? Which is quite amazing. But to use a simple example, if I have two classical computing bits, okay, I could have, I guess, 4 states there, which is 0, 1, 2, and 3, you know?
Right.
Now, at any given time, I guess those 2 bits could represent one of those 4 combinations. Now, with a qubit, if these were 2 qubits, you're saying that they could represent all of the states simultaneously and states in between. How would you explain that to us?
Yeah. So you could think of it as so firstly, like the solution space that you can study because of these qubits and the way they scale is like exponential. So it's something like if you have like 2 qubits, then it's like 2 to the power of n is like how it scales, you know, like the solution space basically. But if in classically, how you can think of it is you would, like each of these states that you mentioned, or each of these, the states of classical bits, you would have to, like in a classical sense, you would have to assess each of them individually, right? But in the quantum regime, you could superimpose all the states together. So basically the qubit, it could be in all these states at the same time. So it has equal probability of being in all the states. And through this superimposition, you can do some really cool stuff.
Yeah. And before we move more into quantum physics, would you say then that quantum computing is inherently more parallel in nature due to qubits and the multiple states? Is that a fair comment?
Yeah, I think you could say so in certain scenarios. Something to keep in mind though, while we're speaking about classical computing as well, is that like quantum computing won't like provide solutions to all problems that even classical computers can. So it's not the case where like in 5, 10, 20 years from now that quantum computers will outrule classical completely. That's something we should get out of the way. There are certain things that classical computers can solve and they're really good at doing, and they will probably forever be good at doing.
Right.
And there's only, a certain class of problems where quantum computing would actually prove beneficial, advantageous, and that would be in certain scenarios where, you have speed ups also, but it would depend on the solution space that you're searching. And yeah, we can get into that a bit later.
Okay. So that's the basics of quantum computing. Let's touch upon quantum physics, because I think in order to really understand quantum computing, you need to have a little bit on the fundamentals of quantum physics. And you've mentioned the three categories, right? We'll start with superpositioning. But before we do that, I mean, I have to say, the first time I looked at it after outside of my varsity physics more recently, really some of this looks like magic, right? Or it's very difficult to not believe, but it's amazing. It's totally different from traditional classical physics. And as a physicist, before we get into these three or four topics, how did you get your mind around it initially? Classical physics, I'm talking Newton's laws, gravity, the bigger stuff, and comparing that to the quantum world. They're just two totally different worlds. And how do you link the two?
For me personally, well, it's hard to say now because it's kind of like I've been studying, this quantum physics and quantum computing, like well, not quantum computing specifically, but quantum physics and quantum mechanics for so long that it's kind of like, wow, it's looking at it or like studying it, it's just like natural now, it's like it's not shocking or like you say, like magic to see it. Yes, it is, but I mean, like it's so I'm so used to it. I don't know if I could put it that way. I suppose at first, yeah, it was a bit overwhelming, but I think when you sit down with it, and I think having the right teachers, lecturers also played a big part in, my understanding and not being like totally overwhelmed by all of its theory. Yeah, having the right lecturers played a big part in it as well. And then, yeah, that's to say kudos to my research group at UKZN, and they are like amazing. But,
Right. Right. And that just made it easier to understand some
yeah.
of the concepts. Okay. So let's start then with superpositioning. Okay.
Yeah.
And you gave out, you touched on it a bit earlier. So what would a more detailed explanation of superpositioning basically be?
Yeah. So let's say for example, you guys know more about classical computing and how classical circuits work, right? But if we have to like speak about the superposition in like the scenario of quantum circuits now, so where you can really see its power is, let's backtrack a little bit. You have something called a wave equation, right? It's something drawn by that psi function.
Right.
And basically, this describes it's a probability distribution, and it describes all the probability of some state or like a system basically, and all the possible states it can be in. And this is cool, but it presents its own problems where we have something called a Heisenburg uncertainty principle, which is like this, yeah, this wave equation is like amazing, but then it has its own cons also, where like through this uncertainty principle, you can only know its position so well, but the better you know its position, the less unsure you are about its momentum, and then vice versa. So it's like
So hang on then. So I remember something from physics, and you must tell me if this is linked.
yeah,
My physics in varsity, there was something called the double slit experiment, which
yeah,
which talked about light. And
yeah,
I remember being fascinated by this, and obviously I haven't thought about this for years, but it showed the dual nature of light, the wave nature and the particle
particle.
particle nature, right? So the wave nature allowed it to travel through the slit, and repropagate as waves on the other side, which is actually mind blowing. And
Yeah,
the photonic experiment, I think, I can't, I can't remember. It's a long time ago, giving my age away, but I think the light particles affected something like a piece of metal by physically coming into contact. So that's the dual nature of light, effectively. Now you're
yeah.
saying that does that have something to do with the states in superpositioning? How is that linked?
Yeah. So basically the double slit experiment that you're speaking about. So you would have like some barrier, but you would have two slits on it. And then you have like these electrons that are being emitted. And basically when both the slits are opened, so what you would expect to see on the other side is straight line and a peak and another peak, but only two peaks, right, in line with the slits. But that's not what you see. You see a wave basically with many more peaks than just two. And that's basically like a probability distribution also. But what happens if you close the one slit and the electrons are only allowed to go to the one, then you see them all clump up on that one spot. So that describes the wave particle duality of the electrons, right? So basically how this relates to superposition, you can think that, yeah, so basically the electrons are going through both slits at one time. That's superposition, which is, it's pretty crazy. Okay, if you have to imagine like observing that in an experiment or like a lab setting as like an undergrad, like, wow, yeah.
And then
So
bringing in Heisenberg's uncertainty principle
yeah.
into that. I'll explain that a little bit more.
So yeah, basically, it tells you that, so again, like the wave equation, right? It's basically a probability distribution. And then from there, you can make measurements of, and there's some like algorithms we can talk about a bit later, I'd like to see this in action. But basically, through measurement, an important thing to know in quantum computing is once you measure a quantum state, it collapses it. What that actually means, we don't know as yet, or like how the state actually collapses, we don't like fully understand, but we know that basically once you measure this quantum system, you won't see the that quantum particle in all states. You will only find it in one state. And that's seen in the double slit experiment as well. It was like we saw the wave, it being in all states, but then once we measured the system, once we closed the one slit, then suddenly it was only observed on one position. So that's basically the Heisenberg uncertainty principle in action, that like you only know, the better you know the position, the less or the more uncertain you are about its momentum, and vice versa.
Okay, so I'm dying to ask you
a lot of words.
There's a few questions that are leading me on from that, right? So firstly, that is part of the magic, what I used to call magic as a non-physicist, right? You saying if I have qubits, the qubits can be in a wide variety of states, but the moment I observe the qubit, it's coming back to me in a state, which could be, let's say, 0.5 or whatever you use. Yeah, one of them. And is it still existing in other states simultaneously, or did me observing it interfere in some way? I can't get my head around that.
Once we measure, we are basically collapsing the superposition, and it's only found in that one state. So this is where things become tricky, but that's basically what measuring the state does. It's kind of like the quantumness doesn't want to be seen, it's there, but like once you measure something, it's gone. So
but is it interference? Is that part of interference? We are interfering with it in some way, or are we becoming entangled? Which leads me to my next question. So what is it? One of those two things?
Oh no. We aren't becoming entangled with the state at all. We are basically just interfering with the quantum physics in general, and halting it right there. It's nothing to do with entanglement.
But even if I'm just looking at it, how am I interfering? I know this might be a very simple question to a non, for a physicist.
It's really actually a non-trivial question. Like I said, we don't know exactly what it means to collapse this quantum the superposition of these states. Why this happens, we really don't know as yet, to be totally honest. Yeah.
It's fascinating.
That's what makes the field so interesting also, right? There's still like so much development being done.
Right.
And now that like we have like there's so much of development on the hardware side of things also. It's not just like all theoretical. Now you can like do actual experiments and see these things happening. You know, quantum computers, they're coming up. They're gonna change things for the better.
I'm just hoping we find some of these answers in my lifetime because, like, I'm literally dying. I'm dying to know, right? Because that's the
Yeah,
first part of magic. Let me talk about the next part of magic, which is even more mind blowing. I want to get to
yeah,
quantum tunneling, right? I don't understand it, of course, I'll admit that. But what I do understand is that you can impact a state somewhere else, or you can entangle. I don't know if the right term is atoms, but you can have quantum entanglement over a large distance. And coming to the real world, what they're talking about now is using this for quantum networks, sending information across vast distances. But basically, it's almost like there's no physical medium. The information just appears on the other side, and sometimes the other side could be, kilometers, tens of kilometers. That's magic, right? You agree?
yeah, yeah, 100%.
You're a physicist agreeing that it's magic.
I, that this phenomena of quantum tunneling is yeah really amazing, and I have to admit I don't study it much. I don't know too much about it, but I do know yeah, so basically it's saying something like there's a quantum state, and then it propagates like through space as far as I know, and then it can reach like something called like a potential barrier. And ideally, like it shouldn't be able to go through there. It should be halted at that point. But through quantumness, some quantum physical properties, it can actually go through the barrier. And I think it depends on the energy of the system, if I'm not mistaken, that the wave can actually continue through afterwards and through that. And that's about as much as I know about that. But I know like with regards to like quantum information, this kind of thing. I think it was back during the whatever year it was that we held 2010 that we held the World Cup here, and my quantum research group, yeah, so they did something at that time through quantum information processing where they were able to transfer yeah quantum information. Basically I think it was from UKZN to or UKZN Westville or UKZN Maritzburg, I'm not sure, to the Shark Stadium. I
Really?
think it was Shark Stadium, something like that. Yeah, it was some distance lesser than around 100, about the order of around 100
So
kilometers
we
or
so we
so.
did this
But
experiment in Durban, in South Africa.
yeah, 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 yeah. So that's some really cool stuff. Yeah,
And
so
how much information do you know, like in classical terms, like a megabyte, a gigabyte, or
to be really honest, I don't know exactly. I just know that yeah, they were able to transfer some kind of quantum information on a significant level and over like a significant amount of time as well. That it was really yeah some groundbreaking stuff. And
and there's no
yeah,
medium
that
in
was
between.
right.
There's no physical line. There's no radio waves. But
True.
isn't that
That's
dangerous? Isn't that dangerous as well? That sounds dangerous because, like,
yeah.
this is
It
this is this is teleportation effectively. Am I right? Do you physicists call it teleportation, or what's
yes. So I think quantum teleportation is different in a sense
okay?
to this quantum information transfer. But yeah, the fact that this was able to be done like physically seen, it was really, really cool. So maybe, yeah, we could do a follow-up chat with, some people in my research group that were hands-on part of this experiment. You could chat with them
I
and I'm
I
sure
would
you.
love that. I would love that. And excuse my very simple questions, not knowing. But as I said, a lot of
Oh,
magic,
no.
right? So, okay, for the viewers now, that's a bit of a discussion on some of the phenomena on quantum physics. And as you said, there's a lot we don't know. What we do know is just amazing. Bringing it back to the real world, it seems like there's actually two things. There's quantum computing, which gives us potentially a very powerful calculation engine, parallel compute, large scale problems, superposition of qubits, and then this phenomena that we've discussed will also allow us to build quantum networks for information transfer over large distances. Could we transfer into space? So let's say we build a base into the moon. I mean,
Yeah,
theoretically, is it possible?
I would say so. Yeah, theoretically.
So
Um,
this could be a way
would
to
that
create a network without, we're not going to have fiber optic cables or
a
something.
quantum network?
Yeah,
Yeah, I would definitely say that there's theory there that shows that it's in the pipeline. But yeah, in that regard, the quantum information transfer and stuff, I'm not too specialized in that field, but I know that there is real research going on. And more importantly, that research is being done right here at UKZN also, which is like
right.
really amazing.
How on that topic, right? Just out of interest, how big is the quantum research team at UKZN? Have they really grown? Is it becoming a big thing?
Yeah. So as far as I know, we are the biggest quantum research group on the African continent.
Wow.
And yeah, so it's really cool to be a part of us. We have our own website, quantum.ukzn.ac.za, if you want to check it out. But yeah, we're such a multidisciplinary field or multidisciplinary group. Like okay, me, like I'm here in I've always been in physics, but like my application, like look, I'm not just doing quantum only. Like I have classical machine learning, which people wouldn't think that we are necessarily doing like in physics. But like, look, I'm merging those two fields together, which is really cool. We have people from finance backgrounds. Optics is really big. As far as I know, we have our own like lab at UKZN Westville where they do a whole lot of quantum optic experiments, which is really cool. Yeah, there's a lot of different research going on, and yeah, we are pretty cool. I like to think.
I know physicists consider themselves cool. It's fine. I'll give you
Yeah.
guys that. Okay, I've got a question on that note, right? So let's move back specifically to computing, right? Mm, Machine learning is a subject that I'm very close to. And I guess now you're going to tell me all the work we do is just going to be called classical machine learning once quantum comes about. But this is very interesting, right? What does quantum computing offer traditional machine learning?
Yeah, so in my okay, just side note, in my particular research, so I model open quantum systems, and then in a nutshell, that just means like it's not a closed system. Like I have some subsystem, and I allow it to interact with some environment and then model its dynamics. And through that, well, actually, my research focuses on like photosynthetic complexes, actually specifically, which is really cool, right? Because I mean, you think like I'm applying machine learning, I'm applying physics, but I mean, like it's something that has to do with like sunlight and plants and photosynthesis, which everybody knows about. And it's basically like we're modeling. We think that the way that energy that's harvested from the sunlight yeah, energy that's harvested by this plant, and the way it's transferred through this light harvesting complex is through well, it makes use of quantum coherence, which is really cool. Like, did you think like quantum coherence is, or like quantum mechanics is happening like everywhere all around you in like a plant, which is it's really really cool. But anyway, so
No, but hang on.
and,
That's an important point. Even though we're
yeah.
discovering quantum mechanics now, the quantum world is the atomic world. Once again,
Right.
if
Basically,
I'm
yeah.
new,
So
it's happening
quantum,
everywhere. If I've got this bottle of water, it's composed of atoms, and
right.
describe it for the viewers, right? So here's a bottle of water. It's made up of atoms, but at the atomic level, the principles of quantum physics apply, right?
Right, exactly. And basically, like, so quantum mechanics, it's this branch of science, right? That's basically models the dynamics of any system that is super, super small, super isolated, and normally super cold. So they work under these totally different laws. It's not like macroscopic on our level, that like it's not like you and I are quantum, but like you said, those like atoms in the water, in those it's the water molecules, those are operating on quantum mechanical laws, which is like really cool. Like basically quantum is everywhere. And that's also like motivation for why it's so important to study.
How come? Very very silly question. How come the water doesn't pop up somewhere else? Like like the
Basically because
information, like the information from PMB to the
yeah.
Shark Stadium. How come?
So Really, really good question. Yeah, if it's everywhere, then like, why isn't, everything, why am I not superimposed and like in 5,000 different locations at once? Yeah. So basically, to observe this quantum coherence, there are super strict conditions only. So for as much as your water molecule or whatever may exhibit some kind of quantum coherence, but for you to observe that, there are strict conditions, and that's maybe I can divert a little and go into like the little that I know about quantum computing, its hardware, is that's what makes developing this hardware so difficult. It's to be able to observe this quantum coherence, like to just name a few, like for instance, the quantum computer itself has to be, or like the chip where this qubit is based on has to be super, super cold. Like room temperature for us is 300 Kelvin.
Yeah.
To observe this quantum coherence, it has to be basically on the orders of a millikelvin. That is like less than 1 Kelvin, which is like super, super cold. And to get to that super cold stage and keep things in that super cold state is a challenge on its own. And then also, the coherence itself is so temperamental and affected so easily by your environment setting, that to keep it clean, keep it coherent is such a challenge on its own. And
So I read somewhere that minute vibrations could actually affect the quantum state, the qubit state. So you need total absence of any micro vibrations. So then the research that you're doing on ML, are you running models on an actual computer? Do we have one in South Africa? Is it a simulator? Tell us a bit about the setup.
Yeah. So my research specifically is again just classic, not to say like just classical machine learning, like it's really bomb in its own sense. And again, like I don't think we'll ever be able to disregard classical computing, classical machine learning in its sense ever. It has its own place. But yeah, my research uses classical machine learning on quantum systems. But to speak about something different, which is the merger of like quantum computing and machine learning. So this I have a lot of, like, maybe my PhD research doesn't, focus on this mainly for now, as it in a sense, but I have a lot of personal and like professional interest in it. So there are a lot of theory around something called quantum machine learning now. It's
Right.
been dubbed that. And basically it makes use of, basically it's a lot of the algorithms now that exist are hybrid. So there's a classical component and a quantum component. So
Right.
like the quantum computer plays its own certain part, and then the circuit, they put together to form the quantum machine learning algorithm together. So like the classical part has its role, quantum has its role.
Let's talk about this, because this is obviously a bit closer to home for me, right? So if I'm building a linear regression model to predict something, or maybe a clustering model where you don't know what you're looking for, and that normally takes up lots of compute because it's evaluating all kinds of probabilities. Okay, quantum machine learning is effectively trying to run this using or utilizing quantum computing, but it's a hybrid. There's, in that ecosystem where you would do it, you'd have a classical component and a quantum component. And is it basically bits of the algorithm run on the quantum CPU, that type of thing? And I mean, but coming back to the question, you guys have a working quantum computer, or is it somewhere else in the world that you connect to? How is that actually implemented?
Yeah, so to start off with that, not that I know of at least, but even my own research team, we are not like actively working on developing our own quantum computer in any sense. So there's something called, through IBM, but there's something called the ARUA network, ARUA, where it allows like most of the big universities across Africa, and UKZN is one of them, that allows them personalized access to certain quantum computers. And as far as I know, IBM has something like a 56 qubit quantum computer available, on the cloud, and it's through that. So whatever quantum experiments or quantum circuits you want to run or evaluate, you do it via the cloud, basically. So there's usually there's two ways of doing things. you could simulate the quantum circuit. Basically, that means simulating it on a classical computer. So that wouldn't take into consideration, like the real circumstances, like with quantum error correction and that kind of thing. And then you can also run your circuits on the real quantum computer where it would, it's real in its sense. It would give you the real quantum output. Yeah.
So I'll just add to that. We also, Microsoft's also offering that via Azure. And
Yes.
we had a milestone.
Sorry, I forget you are Microsoft as well, and I'm just like
No,
throwing
that's fine.
ideas
I
out.
mean, it's about the community, but we actually had a milestone last week where we had we went public, so you can sign up and you can start utilizing quantum computing over Azure from anywhere in the world, right? So I'll add some links for that as well.
Please do.
What's the impact of error correction?
Yeah.
Is that a big thing in quantum computing?
Yep. So as far as to start off with, let's just say, like, I don't know if everyone is aware of this, but having a quantum computer that has more qubits on it does not necessarily make it better. It also means it's subject to more noise, to faster decoherence, to more error rates, and it's harder to manage. So something can't remember exactly like who invented this metric, but it's something called quantum volume, where like it puts maps things against each other, or takes in all factors into consideration basically, and like gives you like the true power of your quantum computer. So yes, in modeling or developing all of this hardware, quantum error correction is really important. So like I said before, these qubits are super temperamental. Putting them into the right environment is critical to actually observe the coherence that you want to do anything quantum in a sense.
So based on what you're saying, it's very unlikely that we'll have a quantum desktop computer. This is a very specialized piece of hardware or sets of hardware. It needs to be at very close to absolute zero, near vibrationless environment, because otherwise there's interference. Because I saw this Chinese company the other day talking about a 2-qubit. I put it on LinkedIn. I'm not sure if you saw it. A 2-qubit desktop computer, but it's quite big. It's like a big heavy box, but portable. And I said to myself, well, I didn't know that was possible. I thought a true quantum computer had these very hardcore requirements. So for the foreseeable future, the desktop computer, the laptop we use, is probably going to be, as you said, classical for a very, very long time.
So in that sense, yeah, I haven't heard of their 2-qubit desktop computer. I'm sure that's really cool. But then another thing is, like how much can you do with just those 2 qubits? Is it really beneficial at all? And then that's also something like worth mentioning, that to be able, well, I'm speaking from my like specialized field of like applying quantum to like quantum to chemistry basically, and quantum biological systems, where like to do something significant, you would need a really significant amount of qubits. And in that sense, maybe keeping them, in the situations where or the environments, the lab setups that they are in now would be best for everyone. They would be more beneficial in that case. And like maybe I highly doubt even in like my lifetime we would see quantum desktops that would really be beneficial or provide like a speed up advantage for everyone. I think working towards quantum computers in a lab setup where they can have like thousands of qubits is a lot more helpful to everyone, research in general.
Okay, so then with that in mind, what are the applications of quantum computing for society? Where will, over the next 10 years and definitely 50 years, where will it be really used?
Yeah. So I have 2 main interests. So, and 2, more of the main fields. Yeah, the fact that I'm interested means that, I research it further, and I'm keeping my eye out in those fields. So first would be in more quantum chemistry side of things, like I said, like my research, quantum biological systems, and the modeling these light harvesting complexes specifically would allow us to create our own artificial light harvesting complexes, and this can be so beneficial, commercially. Another really major thing for us as Africans living on the African continent, like for instance, HIV is such a big thing,
Right.
and to be able to model other biological systems and the way that these mutate, just to be able to why we can't do this classically, I can say is maybe I can show you, send you a link or something and show you that like the size of like the system we can model now is something that with only like 4 molecules and like with a molecule that only has like 3 atoms into something like that. Super simple system. That's all we can do on like the biggest supercomputer currently, classical supercomputer. So through quantum computing, to be able to model more complex molecules would drive research and development in, like I'm saying, for Africans in our African communities. It would drive and motivate, advance HIV research drastically, and many other, conditions medically. Yeah.
Is this linked to things like protein folding? I know a lot of computing was needed.
Yeah.
I used to,
Yeah.
you'll be very happy to hear, I used to donate my computer in quotes, years ago, this was, because you could run an app on your PC that would donate some of your CPU to the folding experiments and things like this. So it's linked to all of that, right?
Yeah. So basically, like we need more computing power, and like I said, like with this 2 to the power of n scaling, we could search a so much larger solution space. And so there are so many like biological, medical research that can benefit from this. And I think that's really at like the forefront. And something like really important to think of is okay, like I'll speak about like IBM, okay, like Microsoft or whatever, where these quantum computers are based. Like there are people in these labs that are, developing these computers and things, but they don't know, they aren't exposed to like our culture, our problems that we have here, they aren't developing it, in the community where we are experiencing these problems. So they're not thinking of solutions to solve these problems. So what's really important for us to think of how we can do our part here on our continent is invest research and proof of concepts now, so that when these quantum computers are available, we are ready to like flip and get going. We have algorithms running, theory ready to be simulated to benefit from these quantum computers. So like it's time to start investing in the research and theory now. That's, if we aren't going to invest on the hardware side of things, then that's where we should be,
Right.
and then another research field or discipline that's really of great interest to me, and this might sound a bit odd, but like finance. So there's so many opportunities and applications for quantum computing in this field of finance. There's so many different quantum algorithms. One, like, I don't know if I can like mention just something like specifically, like a rough example, like how I mentioned HIV in like the medical case. Like here, you could have something called like portfolio optimization. So it's like finding the ideal blend of stocks or equities that would give you the best return. And through quantum computing and again like superposition, you can solve this like really, really well. So that's where I would say, development is mainly my interest is in, and I'm sure there are many other fields also that can benefit from this quantum computing greatly.
Yeah, I think over the next decade we'll know a lot of, we'll understand 3 things in my opinion, right? We'll get a better understanding of quantum physics, all these things that look like magic. Number 2, I think we'll see quantum computing just develop more and more, and then the third thing would be the applications becoming a lot more clearer. So I mean, we'll start wrapping up now. I think we covered quite a bit, especially for the average person to digest in this video. But before we do that, are there any other concepts that you'd like to talk about? Some of these algorithms, like Shor's algorithm, Grover's algorithm, what are they used for? Just very quickly, in summary, just to complete the discussion, and we can then wrap up.
So firstly, like for the I don't like to say, okay, for the average person reading this, right? You don't have to have, or watching this rather, sorry, you don't have to have like any background on quantum physics or anything to start and get going in this field. There are so much of material available online and just everywhere, you know, for out of personal, like professional development, whatever it is, you can get going. It's not too late. Like you don't need to go study a whole undergraduate degree or whatever degree, you know, to understand this stuff, you know. I think if you have like, even that too, I was about to say, even if you have just like a basic understanding of linear algebra, you're good to go. But even that, if you don't have it, you can easily learn that as well.
But
So
on that point, Kimara,
learn,
do you use a
yeah,
lot of mathematics?
yeah,
Obviously, doing quantum machine learning, yes, but even in general, working with quantum computing,
yeah,
is it where you would actually use a lot of maths?
yeah. So on, yeah, in quantum computing specifically, yeah, I think basically to start off with, linear algebra would be really good place to start. But then if you're going to go further deeper into like computational physics and, you know, really, you know, like um, doing your own computing or programming rather to like simulate quantum system physical systems, you know, then yeah, you would use a lot of mathematics, which is really cool. But there's so much of material out there. It's so, I wouldn't say easy to learn. You've got to be dedicated. It's something that you've really got to be interested in and like passionate about. Sorry to sound like cheesy, but you got to be passionate about it to want to learn it at all. And something I wanted to say before chatting about the algorithms is like, yeah, something I wish someone told me when I was in my undergrad is that how useful and how important programming is in its sense.
Really?
And yes, really, wow.
I say really as a former programmer, so it's good to that we have some appreciation, I guess, right?
Yeah,
Even in this fancy
so
quantum world.
lately. So yeah, how can I boil this all down? Like, okay, in my undergrad, I did maybe one first year course on introductory programming, right? And that was Python programming. And thank God that it was Python language because that is mainly what I use now, Python programming. And it
Right.
was only when I got to my postgraduate studies that I was like, yes, okay, you can learn it. Like I said, you can learn anything you want to, but I wish they told us that, and I would have spent more time learning it and investing more time in learning programming because my PhD research mainly, like I am literally programming here. Okay, I use like Virtual Studio. I program in Python every day. And it's taken me a long time to be actual like comfortable with it. Like I like the Python language, and I think a lot of physicists stick with it because it's so user friendly, you know, easy to understand. Like I could send it my code to like a colleague, and they could, with at a reasonable level, they could understand what I'm trying to do in my code.
Right.
And yeah, so if anything, before you even get started in this field at all, like don't forget the programming. It's really important. Find a language that's you're comfortable with. But again, there are so many quantum. Also, like if you want to do any of this quantum computing at all, like implementing it, coding it up, like to say, you have to code to actually implement all of these things. So in case anyone didn't know that, like I think maybe doing it all the time, like I forget to mention that, but yeah, you need to know how to program, which is really important. So
The,
that was, yeah, important
so
side
the
note.
two skills for the average or maybe the young person watching this, Python and linear algebra, right? That's what you're saying.
That would be that, that is what I would say, and a lot of determination.
A lot of determination to understand how the magic works, which I still don't understand. Kimara, it's been so much fun talking to you. I know we had some technical issues, so
Sorry to cut you off. I just want to chat about like something like really quickly,
let's
and
let's let's do it.
yeah, just for those that may be interested, and if they haven't even got bored of me by now, those that have made it to the end of this video,
Right.
that something you could play around with. Yeah, two algorithms that are really cool, and for you to see superposition and interference actually play out in an algorithm, which is really cool. So one would be let's start with Shor's algorithm. So this is really cool, and I think this also attracted a lot of interest because so basically what you can use Shor's Shor's algorithm for is to factor a really large number. So to factor means, to break a number down into, its prime numbers components, basically. So
How large are we
yeah.
talking? Like how many zeros?
So it depends. Yeah, it depends on this, but it scales with your quantum computer. As many qubits as you have, that's as far as Shor's can go, which is really great.
Wow.
So why I was going to say this attracted a lot of interest is because, the RSA encryption algorithm that is basically used everywhere. So people were like freaking out about it because they were like, oh my God, because the basis of it is that factor that the classical algorithm behind it can't factor this really large number used as the encryptions. The fact that like now you had Shor's algorithm that could like factor these numbers, people were like going crazy, like, oh my God, is it going to break like RSA encryption? Not as yet. Let's put it there. Not as yet, and that's only because of the capabilities of the quantum computers available to us for now. So as it scales, as we get more qubits available, then maybe yeah, but not realistically as yet. So that's the cool thing about Shor's algorithm, and you can play with that, play around with that. And then another really cool one is Grover's. So it's a search algorithm, and how a really cool way of explaining it, and I think this is how it was introduced to me, is like, just say you have like a phone book, like a old school thick telephone phone book, and you're looking for someone's number. And or you're looking for the name of someone given their number. And what if that person, the one that you're looking for, is actually the last entry in that book? It would mean you would have had to go through every possible entry. But with Grover's search algorithm, you only have to go through square root of n, where n is the number of entries, which is really cool. If you had to scale that up, like, wow, it would save you so much space. And this is really cool. Like you could do it, like handwrite out this this algorithm for just like a few qubits if you want, and you will actually see through the wave function that I mentioned earlier. It's a probability distribution. So it tells you like the probability, the amplitude in that wave equation will tell you the probability of each state being possible. So while you're like running through this search algorithm, it would actually amplify the correct solution and through interference destruct all of the wrong solutions. So it's something really cool. You can, if you want to see it.
That sounds very interesting. I'm gonna do some research and once again try to understand. Emphasis on
really
try, but you said determination, so I've learned that much from the Shor's algorithm and Grover's algorithm. For those of you watching, very very interesting in the application of quantum computing. Okay, Kimara, I think we're over an hour, but that was a very good discussion. Thanks so much for your energy and explaining these difficult concepts. I think the viewers will really enjoy it. It's still new to the average person, and yeah.
Thanks for having me. I really appreciate it. When I saw you reach out to me, I was like, yeah, I'm so keen to chat about this. I don't get the opportunity all that often, and it's really great. And I hope, even if it just like inspires one person to, start researching quantum computing and play around, like you said, like through Microsoft Azure and IBM, there's so much of stuff on the cloud. Like you could play with a quantum computer like right now from home. So it's really cool. Even if just one person is inspired by this, that I would be like so chuffed. So again, thanks for having me. I really appreciate it.
I'll make sure it gets out and we'll try and inspire the local public, right? So I think if things go well, maybe we can come and revisit some of these complex topics. Perhaps with one or two of your colleagues. It sounds like you've got such a nice team down there in Natal, and I'm very happy because I am from Natal, even though I don't live there anymore. So that's very good to hear that Natal is in the lead. And we can do another more structured discussion with some of your colleagues on one or two further concepts. So we'll look into that for the future. But really, thanks, Kimara, and enjoy your day. And to those of you watching, we hope you enjoyed that, a bit long, an introduction to quantum computing. And we'll see you guys next time. Thanks for joining us.